Alright, this is a Gauss 2026. I'll do everything using my new writing pad and this laptop here. Let's get it started. We're gonna start with this one, okay, 14 here. Before it was a sort of too easy. So let me just copy the thing over. Drag it onto this whiteboard here. Now we can do something. Yeah. How many different 4-digit integers greater than 2000 can be made using each of the 4 digits 2026 exactly once? Yeah, so it is over 2000. That is to say, it's either 2, something, 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 or let's say 6, something, 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 right? You don't have other choices. And if you put 2 in the front, then you still have a 0, 2, and 6. 0, 2, and 6 in any order. So that would be permutation 3. That is 3 factorial. That is 6 of them. If you put 6 in front, then you have a 2, 0, 2, 2. So basically you just want to choose one place for 0. That is 3, choose 1. And that is 3. And then you add them up. That gives you the answer, which is not too hard. This is problem number 14. Yeah, let's clear this whiteboard. Now we go on to problem number 15. Probably we don't need the whiteboard there. Yeah, the numbers on the opposite faces of a standard, standard six-sided die have a sum of 7. Okay, which of the following is not standard? So which of the following would violate, this rule? Let's see. If you have 4 in a row, it's usually better because these two are opposite, these two are opposite. So this kind of structure is harder to analyze. You still can do that, with your imagination, but this one basically requires no imagination. 1 plus 6 is okay, right? 3 plus 4 looks fine, so the rest should be okay. And let's skip this one for now and look at this one. This is a 5 plus 3. Okay, this doesn't work. So actually this is the bad apple. Assuming there's only one choice, one choice that satisfies, then this should be the one. You can also verify, if you do want to, but on a real test, probably you are happy with, spotting this guy. So that is it. That is C for problem number 15. And then we go on to problem number 16. And a game shown, this rear, begins on a start square. This is the start square, and she rolls 2 center 6 sides, 2 of them. Okay, so and moves forward the number of squares equal to the sum rolled, and she continues in this way. Rolling 2 dice and move forward until he lands on or passes the finish square. And if she lands on a shaded square, she follows the instructions shown. So basically she can collect points wherever landed in a shaded box. And if Ria begins with a 0 points, what is the greatest number of points that she can finish with? Okay, good. So the thing is that maybe we're gonna just copy this diagram over. Now look at this thing. So you start with from here. This one is basically 0. Oh no, a pen here. Yeah, this one is basically box 0. You start from box 0, and every time, because you've got 2 dice to roll, so you must move by at least 2. 1 is not okay, or up to 12. Any number between this within this range would be fine, both ends inclusive. So from 0, for example, you're gonna skip this one for sure. You are not collecting the 3 points here. Probably you land at 2. Better yet, you land at 3, right? Let's say, yeah, you are here, you collect this 6 points, and then you collect this, and then you move by 2. You can still collect this, and then you go all the way probably over here. Now these 2 are neighboring. That is to say, if you want to get the 7, then you are going to skip this 8 points for sure, which is not quite a good option. So if you're lucky enough, probably you land here and you skip 7, so you get 8 instead of 7, which is a better result. And then you go all the way down here. For here, now that is the thing. Which one is actually the better choice, right? Which one is the better choice? Let's say at this box 15, you've got x points, right? And here you've got two choices. It is either x plus 10 or 2x. Actually, you want to be lucky enough, so you always get the best choice that gives you the maximized points. And after that, there's no point to collect. And let's say if x is too large, not too large, let's say if x is at least a 10, in this case, 2x would be a better result, right? Plus 10 is not as good as plus x. So in this case, actually, you want 2x. And if x is small, let's say you are not lucky enough, is it possible that this unluckiness is actually a blessing in disguise? So at last you double your points or something? No, this is not actually the case, because if you have collected too few points by box 15, the best you can do is plus 10. So you end up with x plus 10, right? Because x plus 10 is better than 2x in this case. But that is to say your final point is less than 20 because x is smaller than 20. For this case, you have at least 20, and you double it, you have at least 20. You had at least 10, you double it, now you have at least 20. So this is always the better case. That is to say you don't have to sacrifice. It's no point sacrificing any points. Just collect as much as possible, and when you are here, you're gonna double your points, and that is where you're gonna get it. Yeah, and this is probably the best outcome. Okay, this is a very lengthy analysis. I try to be rigorous here. On a real test, probably it's just the intuition that you want to be greedy. Technically, it is called a greedy. So you just you don't sacrifice any points because that doesn't do you any good. So you just collect as many points as possible along the way. This is 6 of them. This is 10, and this gives you 15. This gives you 23. 23, and then you double your points, you get 46, and you make it all the way to the finishing box. So that is 46 points to collect. Do we have actually this 46? Yeah, this is a B. I guess this is the right choice here. Okay, this is for problem number 16, and then it is a problem number 17. Okay, let me clear this board in the first place. And problem number 17, this Asha is asked to cut a 36 meter length of ribbon into smaller pieces so that each piece has equal length and the ribbon width does not change. So the length, so the width actually doesn't matter in this problem. It's just a line segment. You're gonna cut 36 into some equal segments, and the length of each of them must be a whole number. So it's a divisor problem. It's number theory. If she must make at least one cut, so you can't have 36 as a whole. You must cut it. And how many possibilities are okay? So that is to say how many proper divisors of 36. Proper, because 36 is not okay, so that is bad writing. Proper divisors of 36. You don't need to list them, just to do factorization. This is 2 to the 2 times 3 to the 2, so it is 2 plus 1, 2 plus 1. You want proper, so it's minus 1. That is 8 of them. If you don't get what I'm doing here, you just use the you just list all proper divisors of 36. That's not a lot, but this is basically the systematic way of counting divisors. You have like 3 choices over here. You have 3 choices over here. It's always a combination of a number of copies of 2s and another bunch of 3s. Yeah, that is it. So 8, I guess, is the answer. Do we have an 8 here? 8 E. Yeah, that is it. E. Okay, moving on to the next one. Let me first clear this board. I need to do this every time. Cool. This is it. Left 0 point ABC. represent a decimal number. When this thing is rounded to the nearest tenth, so 0 point something a, or maybe a plus 1, just the nearest tenth, right? Just one decimal digit. And the result is 0.024 greater than. Okay, so basically you rounded it up because the result is greater. You rounded it up. And what is the value of b plus c? Okay, so you round it up. Before it was 0.abc, and you go actually this amount higher. You end up with 0. This is a plus 1. This is a single digit, and then 0, 0, right? So basically BC, this BC guy plus this 2, 4 guy gives you 0, 0. That is to see, BC is a 7, 6, so you get a technically 100, and there's a 1 carryover. You don't care about A can be anything except 9. Probably even even 9. This doesn't have to be 0. And let's be rigorous too. This doesn't have to be 0. This can be anything, but it is rounded up. But the thing is that BC is a 76, not 76. BC is a 7 and 6 for sure. So B plus C is 13. This is what is wanted from us. 13, that is C. Okay, this is not too hard. You just need to notice that this thing is rounded up. So just one case instead of 2. Okay, so this thing. Mu chooses a positive integer so that it is between 100 and 199 inclusive. Is divisible by 4. Okay, the sum of its digits is 5 or more. So how many integers basically satisfy all 3 of them? Multiple 4 between 100 and 199, and the sum is 5. Sum of digits 5 or more. Okay, the last one is a little bit tricky, but let's just look at it. First of all, it is between 100 and 199, and this number is a multiple 4, and this sum of digits is at least 5, right? 5, 5 or more, so 5 counts. Okay, cool. So let's say up to a point everything would be okay. So if you got 130 something, probably you're safe, but before that, let's be careful. Like this one doesn't work. 104 is good, so this one is not good. And after that, 10, this 10 row is done, and then we've got 11 row. 11 row has got 112, 116. 116 is okay, and 112 is not okay. This is 4. This is not okay. Then we've got 12 row, 120. 124. 124 is okay. 120 is not okay. So 3 of them, and as long as you have reached this thing, you are safe. And then there's 114 something. You don't have to worry about the rest. This is multiple 4. So 3 are going to be excluded. So how many in total? This is a 100 to 199. Actually not 199. The last one is 196. So the big gap is 6. The small gap is 4. So the total number of gaps is 96 over 4. But there's always one more tree than gaps. So plus 1. That is the total. And then minus 3 of them. That is 22. Right? 22. Do we have this 22 thing? Yeah, this is 22C. Yeah, I guess this is it. Not too hard, just some careful case work. For the first 3 rows, probably you need to eliminate, you need to reject some numbers. And from this point on, you are 100% safe. And then you're gonna apply this gap model. This is the gap model, or the number of terms in a arithmetic sequence, technically speaking. That's it. Let me clear it. Discard. Next one, the dollop sells ice cream cones. Each cone sold is exactly one of the 3 different types: chocolate or vanilla or twist. It's just combined. Of all consoles, 11 out of 17 contain some chocolate, and 10 out of 17 contain some vanilla. If 85 out of 17 cones were sold in total, how many were twist cones? Like it's a Venn diagram problem. Never mind. So, yeah, this is just a. I mean, we are just counting numbers. Okay, we are not sort of like weighing the weight of ingredients or something. So even if you are combined, you would count as one for the vanilla party. You also count as one as a for the chocolate party. I think that is it. So yeah, but let me just copy because there's some data. I want to make sure I don't mismemorize them. Oh no, over here. This is it. No, okay. So let's draw the Venn diagram. Wonky. Let's say this is a chocolate. This is a vanilla. What do we do? Okay. This is a counting. This is 11 out of 17. This is 10 out of 17. So put together, that is 21 out of 17, right? And minus 1, this is 4 out of 17. So this is a 4 out of 17. This is this is vanilla. This is yeah, 10. So this is 6 out of 17. That is 11 minus 4. That is 7 out of 17. That is it. Any problem? No, there's no problem here. Okay. And in total there are 85 ice cream cones. So how many were twist cones? Okay, basically this part. And this part would be 85 times 4 out of 17. That is 20. Do we have 20? Do we have 20? Yeah, this thing E, yeah, should be the correct answer to this problem. So that is problem number 20. Scroll down a bit. Yeah, this is problem number 20. Okay, so far so good. Okay, now we are moving on to part C. Let me first clear the board. This is just a Venn diagram problem. Another way of doing it is converting these fractions to specific whole numbers in the first place. So you probably get 55 for this circle. You've got 50 for that circle. It's still Venn diagram. You can add them up, then minus 85. Essentially the same. Yeah, based on. I mean, it's just a matter of preference. Okay, no big deal. Yeah, discard. And this thing, yeah, it's a geometry. So why don't we just why don't we just copy the whole thing? Right, this thing over here. Good. Cool. Probably I can just work on this diagram. So in this diagram, this is a square with side length 30. This is also a square with UV ampere, so it's all equal. So this is a 10 square. Oh no, pen. Oh yeah. This is a 10. This is also 10, but 10. And what is wanted from us? The area. So the point X is it is just a point so that these two are parallel, right? Tx and WR are parallel. So it's just a parallelogram, and you want to find the area of this parallelogram. Oh, this one. Okay, it's actually super easy. It's just base times height. Base is 10. Height is since this is also square, so this is a 10 and 30, so it's 40 in total. That's 400. That is B. Okay, it looks very complicated. In fact, it turns out to be super straightforward. It is just a B. Yeah, base times height. There's yeah, actually, does it have to be right in the middle? It doesn't matter. I mean, the point I want to make is that you can somehow move this little square on top, left and right. You can move it, slide it along this horizontal line, and the answer doesn't actually change. So it is kind of a redundant information here, or maybe it's just a bluff. I don't know. But sometimes they do include some unnecessary information in a problem in Gauss. Yeah, that happens. So yeah, it doesn't matter anyways. The problem itself is quite straightforward. Okay, just clear the board, and then the next one. This Beverly creates a sequence of integers. She begins by setting sum to 0 and a is 1. Then she writes down the value of the sum as the first term of the sequence, where the sequence, a sequence of it's a bit complicated. I mean, Beverly continues the sequence by applying the following steps. Update sum this way. Okay, sum plus a, write down the sum as the next term of the sequence. And then if a is 9, okay, stops. This is the stop condition, and otherwise a is updated in this way, and then you go back. So, well, this is a this is like a computer science problem, and you've got 3 things to maintain. Basically, you maintain is a word we use in computer encoding or something. Yeah, but basically you want to keep a sequence. You bookkeep a sequence somewhere. That's what we say. You maintain a sequence, and then you update 2 values, which is sum and a. So sum is basically it's just a sum, yeah, and a. So why does this one appear here? I mean, this is just you're just tracking an algorithm. This has very little to do with math, and this doesn't make a great problem. No, but just to do this anyway. Maybe, yeah, some free points for taking, but not a great problem by any means. Yeah, this is it. Yeah, what do we do? Okay, so we've got a few things. Okay, first, probably let me make it smaller because I need some more space here. Should be okay, good. So this is you want to maintain a sequence here, and then you've got 2 numbers. One is a, the other is sum, right? Okay, and you're gonna do it a few rounds, or you're gonna do a few iteration. Yeah, it's a loop thing. I mean, it's all kind of a computer science jargon. You can just ignore on this, but let's just play the game anyways. So first, sum is 0 and a is 1, right? And let's just she then writes down the value of sum as the first term of the sequence. So the first term of the sequence is 0. All we need to do is just play to the book. We just follow the words. We don't skip anything. Okay, we don't want to be creative. Just follow the instructions. Beverly continues the sequence by applying the following. Step 1, sum is sum plus a. Okay, sum is sum plus a. Sum plus a. Now sum is updated to 1. Okay, this step is done. Step 2, she writes down the value of the sum as the next term of the sequence. Okay, this is written as the next term of the sequence, so the sequence is here. Okay, we're gonna separate the sequence thing from the sum thing. I know they're essentially the same, but I want to make the thing very clear, and I don't want to make any careless mistake. So I just do as is told. And then a is 9, a is not 9, so otherwise she sets a is a plus 2. So a is a plus 2, that is a is 3. A is 3 now. And then we go back to step 1. Okay, ignore what is said before, but we just start with step 1. Sum is sum plus a. Sum is sum plus a. Sum plus a now is 4. So sum is now 4. Then step 2, write down the number in the sequence. Okay, write this new sum, this is the 4 in the sequence. Now the sequence is also extended. And then step 2 is done. Then step 3, a is not 9. So again, a plus 2, that is 5. A is now 5. Then step 1, sum is sum plus a. Now sum plus a, sum is 9. Sum is 9, okay? And then write down the number to the sequence. This step 2. Then step 3, a is not 9 yet. So a plus 2, that gives you 7. Okay, then back to step 1. Step 1, sum is sum plus a, that is 16. And then you always don't skip this step. Okay, step 2, this is a 16. Okay, then step 3, a is 9. Is a 9? A is not 9. Okay, so a is gonna be updated. A is 9. However, the step 3 is already done, so you don't stop here. Okay, before it was 7, so you don't stop. You take this branch. So you end up with a is 9. Then you go back to step 1. So again, sum is sum plus a, so you get 25. You get 25, and then you do step 2. It's 25, and then A is 9. If A is 9, you stop. Now you check A is 9. So here you come to a stop. That's it. And now what is the last term in the sequence, which is 25? This is E. Yeah, it can go actually on and on, because this is a perfect square, so you can tell the pattern, because it's just a sum of the first few odd numbers, and that's a arithmetic sequence. But anyways, in this problem, you don't have to do that part. Just to trace, this this algorithm, just to play this game as it's told, play to the book, and then you get 25. Yeah, it has nothing to do with math at all. I don't know. I don't like this problem. It's confusing. I mean, if a computer, I'm sorry, if a student is familiar with this computer jargons, the student essentially knows what is going on here, and the student can just do it with ease, at ease. And if the student is totally, unfamiliar with computer stuff, and the student probably don't understand what's the point of the problem. So this is not a great one. Just like last year, we had a Sudoku problem. The same thing, If the student plays Sudoku, in his or her spare time, then that problem is too easy. Otherwise, the problem is, it's pointless to that problem. It's very bewildering to a student who doesn't play, say, Sudoku or coding. And that's the thing, Probably the problem maker wants to be creative, or wants to integrate some elements from other subjects into this math thing to make it more fun. But I don't see it as a success. Okay, maybe too much yapping. Okay, that's a problem. So I can clear it, and let's move on to the next one. 23. Okay, 2 bowls, each contain both blueberry. Okay, let me just copy the whole thing over, and then we discuss that on a whiteboard. Yeah, okay, good. 2 bowls each contain blueberries and raspberries. In the first bowl, the ratio of the number of blueberries to is 3 to 7. In second, the ratio is 2 to 5, and there are okay, I see. This is a linear combination, but this is a Diophantine equation problem. So you have 2 types of bowls. In the first type of bowl A, you've got 3x and 7x, right? This is a blueberries to raspberries. And for bowl B, you've got 2y, 2 raspberries, 5y. And if the total of raspberries is 89, what is the minimum of this? Yeah, this is a linear programming, but a toy version of it. But anyways, as you know, this is a Diophantine equation. That is to say, you got this in the first place, right? And then what do we do? You've got a bunch of solutions, of course, for a Diophantine equation. So you've got a bunch of solutions. You want to find one that makes this one as low as possible. Since probably 89 is not too large, and this is a skipping by 7, so it doesn't take that long to test every one of them. But systematically, this is probably the better thing to do. You want to find this guy inside this guy, and this is what I mean. So this is a 3x plus 2y times 3 over 7, and this is 3 over 16. Okay, 14. So this is a plus 1 out of 3 y, right? This is to say this is actually 89. This is 89. And so, that's exactly the same equation. This is to say, if you want to make this as small as possible, this one is going to be as large as possible, right? This is the bad thing to do, because the sum of them is fixed. So I want to minimize this part. I basically want to minimize the first term here. So I want to maximize the second term. I want to basically maximize y. So I want to find the solution to this guy so that y is as large as possible. So x in other words, x is as small as possible. So x can be 2. This way you get some 5. That's called 75. So y is 15. This is the best you can do, right? Yeah, that's the smallest solution for this Diophantine or Diophantine equation. So this one would be 3x plus 2y. That is 3 times 2 plus 2 times 15. That is 36. 36 is A, right? Okay, so I think the answer is this thing. Yeah, that's it. So let me look at that again. That is to say you have one Diophantine equation here. The other one is actually because for this equation you're just moving along the line, a few lattice points you're skipping here, and one of them would make this one the smallest. Then how do we find this out? You can do it this way. You can sort of find a few copies of this guy inside this left hand side, and then you have some residue, yeah. And this, if you want to minimize this guy, the rest should be maximized. So basically you use up this idea. You want to use up x, then you have some y copies of y left over, and then you can control, you can basically control y by controlling this value here. Yeah, since the total is fixed. Yeah, that's the idea. But I mean, if you find this one too complicated, that is fine. Or let's say some students just don't like fractions, that is fine. Because for this one, 89 over 7, maybe it's just like 12 or something less than that. Because this is a 35, so maybe just a 2 or 3 different solutions. You can just test them out. That doesn't take very long, but yeah. Anyways, I want to show you the systematic way of doing it. That is it for 23. Okay, let's stop here. I'm gonna do 24 in the next video. See you very soon.